Hello, we're going to start to quantify entropy here and talk about how it's measured as well. So first thing that I want to mention is this fact here. Entropy is temperature dependent, okay? So we've seen that entropy is temperature dependent. Higher temperatures have higher entropies. And this kind of fits in with our particle model, like I've stolen this diagram down below. So when solids are melted, entropy increases, and when liquids are boiled, entropy increases. But within those ranges as well, we saw a nice diagram back here, didn't we? Where we saw that there was still an increase within these phases. So you can see here that this is a positive, I was going to say correlation, let's not overthink that word, but there's a positive relationship even within a state. When it's being heated, you're still getting an increase in entropy. And that's kind of how we think about the particle model too. Let's see how much I can zip back. So let's just think of gases. When we have a gas and we increase its temperature, we're increasing its energy. And how does it express that energy? Well, there's the stretches and the spins and the little wiggles and stuff, but there's also that translational speed, okay? They're moving much faster, and we know from our gas laws too, it's taking up much larger volume, okay? So much larger volume with the same particles equals many more ways to arrange it equals increase in entropy. So when you're heating things, even within a state, you're increasing the entropy. So we have to recognize that that entropy is temperature dependent, okay? And it's going to help us later on when we're dealing with the maths, and we'll see that temperature and entropy go hand in hand together. Okay, so let's start talking about quantifying entropy. Our standard molar enthalpy, and it has that funny little symbol that I don't really talk about too much. I might just add a little bit here. This means under standard conditions like 25 degrees Celsius, 1 atmosphere kind of thing, okay? I tend to kind of skip it, and most people do, but we should talk about it now and then. Okay, I think that's the last of that tangent. The standard molar enthalpy, S, is a measure of the amount of entropy a substance has in its standard state at any given temperature, okay? So, look, here's that graph that I went back to. Entropy changes linearly in each state. That's what I was just saying in the other one. So if the temperature increases by 50%, the entropy increases by 50%. I don't know if that's true, but it's linearly, okay? The units, here's an important thing, of entropy are joules per mole per Kelvin. Okay, so joules per Kelvin per mole, or J over / mole times K. Okay, all right. Notice we don't have a delta for S. Remember when we were dealing with enthalpy, we always talked about change in enthalpy. Here we'll talk about change in entropy from a reaction, but we can measure just S without the delta, okay? We can measure the entropy of a substance. It is absolute, unlike enthalpy, because remember we had no starting point for enthalpy. Even at 0 Kelvin, once we approached it, we still noticed that there was still this energy left in molecules. But here we're defining entropy as something different, okay? A substance has 0 entropy, or 0 joules per mole per Kelvin, as a perfect crystal at 0 degrees Kelvin. So we've got a 0 starting point. So we can talk about the S of a substance, or the entropy that exists in a substance. We've got some 0 that we've assigned, unlike when we're talking about enthalpy. Okay. What else did I see here? With enthalpy, there's still energy within a substance at 0 K, and it's near impossible to measure that, okay? So therefore, delta everywhere in enthalpy. But here, with entropy, we're only talking about a change, or delta S, when we're talking about a chemical reaction happening. So on the left here, I've got my lovely diagram of some repeating structure at 0K, and the entropy must be 0 as well. Our enthalpy, though, we don't know. It's greater than 0. It's something, we think, okay? But it's very hard to measure. Well, very hard to measure. It's impossible to measure and guess at, okay? So entropy change. Remember, the entropic drive is when the entropy change increases, so it's greater than 0. So this can happen in both physical and chemical changes, okay? Could happen. So the standard entropy change for a reaction is the difference between the entropy at the end of the change compared to the beginning, and now we bring in our delta, okay? So our delta S is equal to the entropies of the products minus the entropy of the reactants. Notice some mirroring here of how we calculated like the heat of enthalpy of a reaction from the heat of formation values. Okay, similarities, mirrors. Okay, so we do the sum of the entropies of the products minus the sum of the entropy of the reactants. And then if delta S is less than 0, well, the entropy for the reactants must be larger. Okay, so entropy decreases through the reaction, so it goes against the entropic drive. Remember, we said that can still happen. Okay, if S is greater than 0, the entropy of the reactants is smaller and the products is larger, so the reaction is becoming more disordered. Okay, so to get these values, we just look them up. If you're doing some real-life chemistry or real-life problem solving, we look them up, okay? Here I've just stolen the table from the textbook with some values. We'd look them up in a textbook or look them up online from a reputable source. If we're in the exam conditions, we don't get that on our data sheet, so that means they will have to give us an entropy value if we're going to use it in an exam, okay? You can't guess them, you can't calculate them, they've got to give them to you. So, example 1, calculate the standard enthalpy change for the reaction of, we've got 2 moles of carbon monoxide and 1 mole of oxygen gas combining to form 2 moles of carbon dioxide. Okay, so our formula for delta S, so calculate the standard enthalpy change, delta S, equals the sum of S of the products minus the sum of the entropies of the reactants. Okay, and you can kind of treat it, it's going to be the same way as how you treat calculating enthalpy from heat of formations, as I said earlier. So I'm going to start with my brackets, and I'm going to talk about we need 2 times the entropy of carbon monoxide plus 1 times the entropy, or you know what, get rid of the 1, we'll be right, plus 1 times the entropy for O2, and we're gonna minus, I was meant to do products. Look at me making the silliest mistake ever. You've probably been screaming at me. Okay, I did the reactants first. What a numbskull. Okay, 2 times the entropy of carbon dioxide. That's our products. Oh, I don't even know my products from my reactants. Okay, 2 times the entropy for carbon monoxide plus 1 times the entropy of O2. Okay, remember back how we had the heat of formation stuff and we had some 0 values in there? We don't really have any of those now. They'll all be given to you in a question. So we just need to find them on our table. So 2 times, well, what's the entropy of CO2? It's given down here is 214 joules per Kelvin per mole. 214, I'll put my units in last, minus 2 times, what's the entropy of CO, or carbon monoxide, 198, plus 1 times the entropy of O2, which is 205, and my units are joules per mole per Kelvin. I like to write it like that. And now I'll get my calculator. So be careful of, well, most of the entropy values will be positive. A couple could be negative. Let's not go there. So you don't really need too much to keep an eye on your double negatives here. So 2 times 214 minus 2 times 198 minus 205, and I get negative 173 joules per mole per Kelvin. So delta S is less than 0. So entropy for this decreases. And we can kind of estimate that actually, looking at the top there. Hang on, we had 2 moles of a gas plus 1 mole of a gas, making 2 moles of a gas. So 3 moles of a gas going to 2 moles of a gas. We would estimate that using our previous skills. We'd go, hey, that's decreasing in entropy. Now we've got those values, we calculated a tick. That's good. Phew. All right, example 2. Calculate the same thing. We've just got a different reaction here. We've got the combustion of hydrogen to form water. Okay, let's start with our, getting a pen, let's start with our delta S. And it's going to equal the sum of the entropies of the products. Hopefully I get them around the right way this time. The entropy of the reactants. Okay, so my products are all 2 times the entropy of water, and that's my only product, minus 2 times the entropy for H2, plus, oh, I was going to write 2 times, I've only got 1 mole of the O2, the entropy of O2. Close your brackets. Okay. 2 times the entropy for water is just here. Oh, is it gas? Whew. Check your state too. See how they're slightly different? Okay, so for water, gas is 189 joules per Kelvin per mole. Minus 2 times the entropy for H2. There it is right above, 131. Plus the entropy of O2, we used that before, didn't we? Which is 205 joules. Confirm me now, pen. Joules per mole Kelvin. Put it in your calculator. 2 times 189 minus 2 times 131 minus 205. Negative 89 joules per mole per Kelvin. So another one that is less than 0, or it's becoming more ordered. Let's have a look why. Because we've got 3 moles of gas going to 2 moles of gas again. Okay, so our estimate would have been that the entropy was decreasing, and we've shown that mathematically. Alright, if you need some more problems, there's some from the textbook. We'll start the next video there.